In this video, we demonstrate LAPP, Large Language Model Assisted Preference Prediction, a new learning framework that enables reinforcement learning agents to acquire complex, customizable behaviors with minimal human supervision. The core idea behind LAPP is simple but powerful. Instead of relying on handcrafted reward functions or expert demonstrations, we leverage large language models to provide preference feedback directly on raw robot trajectory data. Let's walk through how this works. We begin with an agent interacting with its environment using an initial, possibly untrained policy. This generates a set of state-action trajectories, essentially short clips of robot behavior. We then query a large language model, such as GPT-4, to decide which of two trajectories better aligns with a high-level user intention, described in natural language. Notably, to enhance learning efficiency, we encourage the LLM to generate adaptive evaluation criteria, allowing the LLM to dynamically adjust its preferences as training progresses. For instance, in quadruped locomotion, early-stage training should prioritize learning to stand, followed by developing stable movement and ultimately refining gait patterns and command adherence. Instead of providing these stages explicitly by humans, our prompts ask the LLM to actively decide the important factors for different training stages by itself. These preference labels are used to train a preference predictor, a lightweight neural network, or a transformer model depending on the task complexity. This model can then evaluate new behaviors and generate dense preference signals for reinforcement learning. In this way, LAPP creates a closed feedback loop. The agent explores the environment, the LLM provides preference comparisons, and the preference predictor updates the agent's policy accordingly. What makes LAPP particularly effective is that it allows the user to define goals in flexible, high-level terms, such as walk with a bouncy gait, move quickly while keeping balance, or flip backward with style. As training progresses, the agent refines its behavior to better match these intended qualities, even in tasks where reward functions are hard to specify. Here, you can see LAPP applied to both quadruped locomotion and Dexterous manipulation. In each case, the agent learns to perform increasingly complex and aligned behaviors, guided purely by language-based preference signals. Notably, LAPP enables impressive behaviors like a quadruped backflip, which are difficult or even impossible to train with standard reinforcement learning alone. In summary, LAPP offers a scalable and generalizable way to teach robots what we want, not through tedious engineering of reward functions, but by expressing our preferences in language. This bridges the gap between natural human intent and effective robotic control, enabling more intuitive and versatile robot learning. For more information, please refer to our paper and project website.